All right, so for the hands-on, do you guys have the link for the GitHub? Let me just pass you that. Download the two files. We won't have time to go through the problem yourself, but at least we'll run the circuit ourselves and see how it works. Okay, so I'll put it on the chat. Okay. Yeah. All right, so can you guys go to, okay, so let me do it myself so that, okay, Zoom, share screen, step one, okay, very good. So if you go to this GitHub, right, Pawsey Bootcamp 2024, week 1, go to QFT hands-on, and then download these two files, QFT intro and QFT solution, okay? And then go to this Amazon Braket, open your notebook that you had yesterday. So open this Jupyter Lab. Okay, and so I created the folder myself, but you can create a new folder like this, and then rename it as QFT hands-on. I call it QFT hands-on, and then copy your wherever you downloaded it. Copy your, okay, so this is QPE. Sorry. Yeah, copy these two files on the folder that you just created, okay? Week 1, QFT hands-on, yeah. So copy these two folders, these two files, okay? Okay, can anyone give me a thumbs up after they're done with that? Okay, taking time. Yes, thanks a lot. Yeah, so click on this link. Okay, so if you don't have access to this, yeah, click on this link, join event, sorry, do this join event. I'm sorry? Click on this open AWS console and go through the steps that we went through yesterday, okay? Link to AWS environment, okay. Let me just do that. Yeah, so this is the console. This should be standard for everyone. Click on this. Okay, so let me close everything. Yeah, so click on the link that I just shared. And then click on Amazon Braket. Click on notebooks. And start the notebook environment, notebook instance that you created yesterday. If you don't have it, then click on this create notebook instance. Okay, so because I have it open already, I can just open this URL. All right, and then download the files from the GitHub and then upload it there. All right. Can anyone? How are we going with this? Okay, take some time. Please ask questions. Okay, like, what step are you in? Are you downloading the file? Do you not know how to upload files online or whatever the question is? Please unmute yourself and feel free to ask. What's the difference between circuit and circuit? Oh, okay, sorry. Just ignore the first one. You actually don't need this. I think these are two different libraries. Was updated since yesterday. Yes.
We'll be updating.
Just speak from here.
We'll, we'll be updating the GitHub repo every day as we put in the hands-on. So yes, so please do log in to download it, or if you're using GitHub, please pull the origin every day to download the new hands-on for each day.
Yeah. So the GitHub will be updated periodically. Okay. Yeah. We would have liked to use start a conda environment, do git clone and all that, but we thought this would be the simplest for people who are not familiar with the Git environment. Okay, so someone asked what's the difference between circuit and circuit. Just ignore. So here the circuit is initialized, right? This capital circuit with capital C. This is an object. If you initialize it, then you create an instance of the object. Okay. So what we're doing here is this build QFT circuit takes the number of qubits as input. Okay. And the range. Okay, so let's run this. Okay, it takes a while to load. Okay, it runs. Okay, so you can click on the on this notebook column and press A, or you can press on the right and then can create a new cell above. That's also fine. So I just like to press here and then press A. And this, if you're not familiar with what is going on here, just print it out, right? So just copy it, apply something like 2, and you'll see that this just gives you numbers from 0 to 2. And then if you create a list out of this, then this will give you a list of numbers of size 2. Okay, so if you do 4, it will be this. So here we're just creating a list of the circuits. Here we're instantiating this circuit. The full circuit that I showed you, here what we're doing is we're iterating through the target qubits. And then here we're iterating through the control qubits. Okay, so remember that the target qubits are where you apply, where the 2-qubit gate is applied based on the control qubit. So as an example, let me go back to my slides and look at the circuit. So if you look at the circuit, right? So for example, here, the second qubit is the control qubit, the first qubit is the target qubit, the third qubit is the control qubit, the first qubit is the target qubit, so on and so forth. So if you look at this circuit, it has a pattern, right? It has a recursive pattern, and we are basically coding this pattern here by iterating to the target qubits and the control qubits. So if you look at this, when the control qubits and the target qubits are the same, I'm just applying the Hadamard gate, right? So you just need to apply Hadamard. Yeah, so I'll just copy it from here. Yeah, so just apply Hadamard gate when they are the same. When they're not the same, then what do we need to do? When they're not the same, I need to apply this control phase gate, right? Which is this guy. So I need to define my angle first, which I do here, and then apply this control phase gate. Okay, so the angle is defined like this. Notice that I have pi over 2 to the power of the difference in the qubits number, and then I just apply this control phase gate. Okay, and this is the part where we add the swap gates. So yeah, the way swap gates is added is again, you have two qubits list. So the first one is the control qubit, the first qubit, this is the second qubit, and this is where we apply the swap gate. I'm swapping between the first and the last bit. So I do this by doing this -1. So please look through the code yourself later on, and make sure that you can try and fill it up. If you cannot, then please look at the solution and make sure that you understand every single line of code, essentially, what is going on. Okay, so because we're out of time, I'll just run simple examples. Okay, so if you look at this solution circuit file, okay, so let's do QFT on, let's say, 3 qubits. All right. So you build the circuit. This is what this function build QFT does. Okay. I print this circuit out. I can also do the inverted QFT circuit by just doing this adjoint function. And then I can start with my circuit, and then I can add the initial state and the QFT circuit. Notice that this initial state is essentially empty if you have nothing. So right now, this is just an empty circuit. So the initial state is nothing. But you can specify what you like your initial state to be. So feel free to play around with that. But if you just run the code as it is, yeah, you'll get this. So if I start my initial state as 0, 0, 0, which is the empty. So if I initialize all these qubits in the 0 state, then if you go back to the circuit, then that means all of these control gates are not applied, right? The control gates are only applied when the qubits are in one state. But if you initialize all qubits into the 0 state, then only the Hadamard gates are applied. And what do the Hadamard gate do? They create a uniform superposition of all possible states, right? Which is what we see here. Okay. And this is the second test you can run to make sure that QFT circuit and the inverted QFT circuit cancel each other out. So if you actually run this, you should get to a case where, yeah, you should get to the initial state, right? Because QFT and the inverted QFT should cancel each other out. And this should be a final state vector. Feel free to play around with this by starting from a different state or applying a Hadamard gates in the beginning. Oh, I still have 15 more minutes. Oh, okay. This is great then. Then we can go through this step by step. Okay, this is great. Sorry. How to interpret the result if they are all equal probability? So if they are all equal probability, then that means that, so in this case, right? So remember, QFT is a map that takes your initial state to some different state. Okay. So what do these probability mean? The probability outcomes correspond to the amplitudes. So these probability outcomes correspond to the amplitude here, right? So if the probability is the same, then that means that all the amplitudes should be the same, right? So that's how we interpret the result. Okay, so you go from the probability, which is a number, to this amplitude. Okay, and we can go back and forth, right? You can go in either direction. Okay, so because I thought we're out of time, but we're not, so we can just go through this step by step. So okay, let me ask a question first. Do we have this notebook? Do we have the notebook on? Test the Jupyter notebook on Pawsey quantum server, or can it only run on AWS Braket servers? So the reason why you're using this AWS Braket server is because so actually it should run on your local environment, which means it should not just run on Pawsey server, but it should run on like any server. But we don't have the AWS library installed. So if you want to run locally or on different server, then you'll need to do pip install AWS. And then you can run this. If you're only using no code streams, is an AWS account not needed? Yeah, that's correct. You don't need an AWS account to run this locally. But the reason why we recommend you to do this is because tomorrow onwards, we'll be using the hybrid jobs where we'll not just be running locally, but also running on the server. So we're just developing the habit of doing this. So another thing I should also tell you is that you can also create your AWS account, and you can set up an environment where you install certain libraries on your terminal, and you can actually work from your terminal. So I have a working environment, for example, on my VS Code. So I can actually access the AWS server from my VS Code. So I don't actually need to start this notebook. And just to let you know, remember that instantiating this notebook actually costs you money. This is charging you some cents per minute. So after this session is over, after 2 days, I recommend you to not use the SageMaker actually, but start your environment offline like I do, and then access the cloud. Okay. Okay, so does everyone have the notebook with you? Okay, Alex says yes. I see another thumbs up. Christopher says yes. Zess says yes. Okay, excellent. Very good. Emily says yes. People who are not giving a thumbs up, does that mean you don't have the notebook open? If you don't, then you can say I don't. That's fine. Then maybe I can help you. The rest of y'all, do you not have the notebook open? Oh, who does? Anyone who doesn't have the notebook open, please. So if you don't say anything, then I'm gonna assume that you have the notebook open. Okay, so and it's not helpful. Okay, so I'm gonna assume that you have the notebook open. Not yet. Okay, so where are you stuck? Can you tell me where you are stuck? Yeah, you need to get to a state. Okay, so people who have the notebook open, please start working on the problem. Look at the intro file, um, and start filling up the code. Okay, people who have the notebook open. People who don't, yeah, please text on the chat, or just unmute yourself. And if you have the problem with getting to this stage where you have this Amazon bracket SageMaker open or anything else, please let us know. I think tomorrow onwards, what we can do is before we start anything, let's just get to this stage where everyone has the code ready in the beginning of the day, and just keep it open throughout the day. Okay. If you don't have this open, then you also won't be able to run the other hands-on sessions that will happen later throughout the day. So you have to have this prepared now. Okay, so I'm just gonna go through the notebook now. Okay. Okay, so yeah, okay, let me again restate what is going on here. So first is we're iterating through the target qubits, and target qubit is for the purpose of applying this control phase gate. Okay. And then we're iterating through the control qubit. Okay. So if the control qubit and the target qubit are the same, then we just apply the Hadamard. If not, then I apply this control phase gate, right? The way it works is it asks you to specify what is the control gate, what is the control qubit, what is the target qubit, and what angle do you need to use, okay? And then what is happening here is I am trying to apply let me go back to my slides. Okay, so I don't have the swap gate on my slides. But what I'm trying to do is I'm trying to, let's say, apply swap between my first qubit and the last qubit, right? So what I'm doing is I'm iterating through half of the qubits. And I'm saying that the qubit, so for a given qubit index, it needs to be swapped with negative of the qubit index -1. So as an example, let's say if your qubit index is, let's say 0, then 0 is being swapped with the last state, right? So -1, for example, in Python, if you have an array, 1, 2, 3, something like this, if you call array -1, then this will give you the last number. Okay, so what I'm trying to do is I'm trying to swap between the first qubit and the last qubit, and then the first qubit and the second last qubit, and so on and so forth, right? So this is what is happening here. Okay, is that clear? Is everyone on the same page with me on this? Okay, delete this. Anyone with any question about this function, build QFT? No questions? Okay, so should I assume that everyone understands this? Okay. Unfortunately, that's what I'm gonna assume because everyone is silent here. Okay, so this build initial state, right? So what is going here is I'm again like preparing my qubits. I'm instantiating the circuit object. And if I don't want this, don't want to initialize the qubit in any state, then I'll just leave it empty, which means it's just the 0, 0, 0 state. If you want to start from any other state to play around, then you want to fill it up. But for now, you can just leave it like this. And let's say you started with 4 qubits, then this would look something. Oh, why is this not printing? Oh, because this circuit is empty right now. That's why it's not printing anything, okay? And then if you call this on the first qubit, what I'm doing is I'm running tests, right? I wrote my code, which is just this simple circuit code. I need to test my code, right? And the first thing I need to check is when I'm running a qubit with empty states, which means all the 0 states, then doing the QFT just applies Hadamard gates only. And I would expect to get the uniform superposition state, right? So here I'm building the circuit and I'm printing it. Here I have the inverted circuit as well, and I'm printing it. And you see the Hadamard control phase is applied, and then I'm doing swap at the end. And this is just reversed with the inverted circuit, which I'll use later. And then here, yeah, so here I am basically I'm asked to add QFT circuit, right? How do I add a QFT circuit? So if you run this, you'll get an error, right? Because the F1 is not defined, but you need to call the function that you need. What function do I need? Anyone? The function that I need to add the circuit is just add circuit, okay? And I just take this circuit and I add it here. All right. And so what I'm doing after this is I'm doing circuit.state vector, which is where I'm specifying that I want the full state vector. Here, notice that I'm not doing any sampling. Sampling as in I'm not specifying how many shots I need to apply. I'm saying that I want the full state vector measurement. And so this is the state vector simulator part. Here, actually not measurement, but you're actually getting the probability here. Okay. So if you didn't know how to get the probability, I think you can just call circuit.probability. Yeah. And if you run it, you'll see that I have a circuit, and then this circuit will return me the probability outcome. Okay. So here I'm specifying I want the full state vector. Here I'm saying I want the probability amplitudes. Okay. Any questions on this? So this is just using the AWS. You'll need. I am also not familiar with this, but you just need to look at the documentation and specify what you exactly want to get. Okay, so you can do density matrix here if you want density matrix, which we will not get into, and so on and so forth. Okay, after this, we need to run the task on the device. So okay. Got it. So it took a while to get on the dashboard side to eventually get to the notebook. Okay, that's great. Please fire up the Jupyter Lab and keep these two folders open. Okay, so this is just running the tasks. So I'll just go to my solutions code and then get the answer from there. So if you are starting out, please look at the documentation and then specify exactly how you get the task and the result. So the way you get it is, so in AWS, task is defined as something that you run on your device. So what you do is you do device.run the circuit. You can specify how many shots you want to run, but because I want the full state vector, I can say shots equals to 0. That means that it's essentially equivalent to saying it's infinite number of shots. The reason for this is you can also apply finite shots if you want, but because I specify the full state vector here, I'll just do it without specifying finite shots. Okay. Please play around with this hyperparameter and see how the result changes. Okay, and you can retrieve the result from the task as result.tasks. And then from this result, you can get your state vector and your probabilities amplitude by simply passing a result here. Maybe it's result.values. Yes, result.values. Yeah. Okay, so if you call result.values, it'll give you two things. One is it'll give you the state vector. And state vector has these amplitudes, right? These complex numbers. And if you norm square those complex numbers, you essentially get the probabilities. And this is the case where we have the, so if you just do this and then plot it out, this is the case where we had this uniform probability, right? After applying QFT, which is what we would expect if we started from the initial state 0, 0, 0, because only the Hadamard gates are acting, right? Okay, just note that there is, yeah. So because I'm running on a local simulator, which has no noise, so if I'm running on a local simulator, so then I don't need to specify shots. I can if I wanted to, but I want to get the highest level of precision as possible, so I'm specifying no shots. But on a real device, you don't have that privilege, right? So on a real device, because you work by applying shots one at a time, so you can only get finite shots there. Okay. All right, so this is the second test I have. So the code that I wrote here could be wrong, right? Or you write could be wrong. So to test that, I need to also make sure that the QFT circuit that I defined here and the inverted QFT circuit that I defined here cancel each other out. Okay, so I should, whatever state I started with, I should just
Yeah, sorry. There seems to be a technical issue. Dikshant is still with me here. I think you can just. Yeah.
Okay, I'm back on the good background.
Right, so we momentarily lost.
Yeah, my computer just.
Oh, yes, computer.
All right, okay.
Yeah, okay.
I will mention.
Yeah.
Yeah. Yeah, I mean, I don't have a computer, I guess. Okay, guys, so please run the notebook. We're approaching the end of the lecture anyway. Make sure you understand it. And if you have any questions, please feel free to ask. Okay, thanks a lot.
Dikshant, are we going into a break now?
Yeah. Hi, Fatima. I think we'll let people play. I'll double check with Dikshant. You should be able to join us
Okay.
as well.
Right, yeah.
Just let me turn on video so people can see me as well. Just to know, as you're playing, really try playing with the setup because it's kind of gives you a sense of the hands-on. The simulator, just to give context, if you try the simulator, you get some results. They're exact. You'll always get the correct answer. But if you start doing stuff with real simulations, you have to put shots, the noise, the gates will also have different noise. So it becomes a bit more complex to actually verify quantum circuits, but also try doing silly things like scaling and asking for enormous sets of circuits. You'll get just saying no. Really play with the workspace and the QFT.
Sorry. There just seems to be a comment on the chat. So Sharif, change your input states. Try playing around with different input states, and you won't get 0, 0, 0 if you run them.
All generally the idea is that input states are all initialized at 0, 0, 0. They're just all initialized at 0. That's not necessarily true for some devices where you would have to imply putting states in 0, because some things set up. But like if you're running simulators, they always just assume that everything's initialized in the 0 state.
Yep.
And remember that you can just apply some gates, right? So you could just do like an X gate, the bit swap gates to do a specific representation of a number.
Yeah, and any other questions? Okay, I see another. I still cannot get the interpretation of the result. Let me apply FFT 0, 0, 0. I get 0, 0, 0 for the classical outcome. Oh, so remember that the initial state is initialized to be 0, but the thing that you're doing in the circuit, so you have the Hadamard and the control phase gates, right? So right now what you're doing is you're trying to compare FFT on bit string 0, 0, 0, and then QFT on the state 0, 0, 0. And that's not the right comparison you should be making. So try, what about you do this? Try applying FFT on a number, and then take the binary representation of that number, and then apply the circuit with QFT. And then look at the probability amplitude and see if you can make sense of it. I like that you are trying to make this comparison because it's very important, which I didn't do.
I think one important limitation of a QFT as well that is not really, that we didn't really go through as well, especially when you compare to DFT and QFT, is that the QFT is also really only available for use on the quantum computer. After you run the circuit, you don't really get, you don't really get to, unlike the normal DFT and FFT where you can run it with a classical computer, you can't get the results of the QFT. You can't take that. You can't take the nice state that is already in and then use it in a classical computer. So that's one very important limitation for the QFT as well, that you have to remember, especially when you start comparing it to FFT and DFT.
Yeah, and we'll get into this all this problem with loading classical data. So that's one big problem with quantum computing right now. It's an open problem, which is let's say you have an image that you want to do Fourier transform on, right? It's a classical data. To load it into a quantum state, you actually require an exponential resource there. And the advantage that you get from quantum algorithms is it's sort of lost, right, in a way, because you had to apply this extra resource to load the data. So yeah, in this case, the direct comparison is not there. But just remember that you're working with two different domains here, classical and quantum. And so this quantum Fourier transform is a very important subroutine that for other algorithms that will follow. So it's really important that you understand. The hands-on is just a way for you to digest what you learn. But what is really important is how you constructed the circuit and how you got to the final circuit. That's really important to understand.